Log on, tune in, find out. Another good idea from Cambridge.
This Industry Day. I'm Rosemary Bailey. I'm one of the organisers of the programme that's happening here at the moment on design and analysis of experiments. And some of you who've come here just for the day are saying things like, gosh, how does this work? Are you here for a week? The answer is no. It's wonderful. If you want to, you can be here for 5 months and just concentrate on doing your research and design and analysis of experiments. And of course, deal with the questions you get from people in industry or people in other scientific subjects who want their experiments designed. Anyway, before I pass on, just in case there was anyone who wasn't here this morning, to remind you, the talks are all recorded. All these microphones here are for that purpose, but that does have the downside. If anyone has their phone switched on and any incoming signals come, we get horrible beeps from all of these. So please, if you've got a mobile phone, please don't just switch it to silent mode, please switch it completely off. And with that, I'll hand over to Martin Owen and Kate Llewellyn from GlaxoSmithKline, and they're going to tell us about from ideas to implementation. We're going to get a double act. Martin, I think you're starting.
Thank you very much. It's a great privilege to be here today, and thank you very much to all the organisers for setting this up. You'll see that I'm very excited about the possibility of collaboration, and particularly having industry and academia in the same room is actually really important to me. The main theme of this talk, it picks up a lot of the aspects that were described this morning by Tim and Justin in terms of the cost of experimentation and getting a better return on investment. So this guy, Ronald Fisher, back in the 1930s, came about with the idea of experimental design, and just like in Tim's talk, when he talked about the theory that was developed in 1914 and he picked it up in 2004, what's interesting here is that experimental design was around for a long time, but I'd worked in industry for 15 years and I'd done a degree in chemistry and I'd never come across it. The moment though you do come across it, you realise that actually, because you know what experiments you're going to do in advance, you can start to think about the possibility of automating them. So it wasn't long before we actually had the idea of combining experimental design and automation, and 6 years later, after I'd come across the idea of experimental design, we'd built this robot. It's £1 million. We'd invested that. It took us 2 years to build it, and we were in the position where we could do automated experimental design. Now, this idea that we've just talked about the ideas and how important it is to go from the transitioning the ideas to actually where they add value in the workplace. And my role within GlaxoSmithKline is the quality by design innovation leader. And what I'm doing is I'm looking at what's happening outside the organisation. I'm looking to see what the creators, what new ideas they come up with. So admittedly, Ronald Fisher's idea of 1930 wasn't a new idea, but it's about looking outside the organisation and seeing what's happening outside. And then looking at how we actually translate that idea into something that is relevant to GlaxoSmithKline, how it actually could be applied in our world and our organisation. And the navigator aspect of leadership is actually looking at when to apply these models, when to apply this type of process. You know, does it make sense to apply them just as the drug has been created, or does it make sense to wait until the drugs are on the marketplace and then apply these techniques then? And then really the importance of the stabilizers, who are not really looking at, you know, the most new and exciting ideas in the organization, but looking at how you can actually take these ideas and stabilize them so they become mainstream. So you use them, you know, as part of the way we work in order to add value. And there's the idea that as you go along this axis, it's all about the context of where you're going to apply the ideas, and across this axis, as you get towards the stabilizing it, it's more about discipline. So once we'd got the robot in place, we recognized the importance of doing sequential experimental design. And at this point, when I talked to Sue about this, Sue mentioned, don't call it sequential experiment design, call it, I can't remember what she asked me to call it, but the point was, the reason there was some confusion is that each of these dots we call an experiment, where, whereas it's more conventional, I guess, for a statistician to call these 4 experiments as opposed to whatever there are 60 odd experiments on the board. So immediately, in terms of actually understanding how we're going to apply these things, you have to recognise that there's different ways of thinking across the disciplines, different ways of terminology, and part of the actual getting to grips with whether an idea or not is going to be useful for you is you have to get through some of those hurdles. Now we have the robot in place. We could do, say, 4 experiments at the beginning to determine whether we've got the ranges right. We'd then screen lots of factors and determine which factors we were going to look at. We could then augment them. We could then add additional reactions to get a more predictive model of experimentation. And then finally, we could move into a robust area and demonstrate that no matter what variations we made deliberately, all our reactions still pass the criteria for success. So once we had the robot in place, we could recognise that we could do, say, the scoping on the Monday, screening on the Tuesday, optimise on the Wednesday, and the robustness on the Friday. So we could actually run through a whole series of experiments and build up this big picture of process understanding. And that's all very well, because we've got the cost of experimentation is reduced, and so we can do many experiments throughout the week and build that up. But what we realised that as we went through this process, you could actually create good designs with less experiments. So the fact that we'd actually done all these experiments, we were now in a position to be able to look at what would have happened if we hadn't have done some of them, if we'd have done more aggressive fractionated designs, for example. So, and of course, so before we go into this, the key thing at this point was that we'd run through these sequential experiment design, and it was all about adding value. And the way that we chose to do this, we started working on existing manufacturing processes, and we could find that by actually looking at the existing process and applying experimental design to it, we could improve processes. And we were getting processes improved by, regions of £1 million, £3 million, and we did a piece of work that was up to £7 million. So even though it appears that experimentation was expensive, the return on investment was actually quite powerful, and that's a very nice place to be. Having got these models in place, we then started to put them into simulations. And once you had them in simulation, you could go into the classroom and you could get people to actually look at a 4-factor problem, see what, press the button at these settings and see what the results would be, get them to alter the settings, press them again. And we use this as a basis of workshops that we use to teach experimental design. And we have, as I say, we've put a number of our case studies into these simulations, and people can experiment in the classroom. And the beauty of it is that they can try different strategies out. And over the course of a day, what's kind of slightly alarming us in a sense is that what took us 3 years to actually get to grips with in the laboratory over a long period of time, people could actually experience that in the space of 1 day. So you can really compress the rate at which you experience and which you can take up the ideas. And also, obviously, if you do make a mistake in the classroom, it's all you've done is you've moved electrons around on the screen. Whereas, obviously, if you make a mistake in the lab, you're talking about we've just lost £10,000, we've just lost £20,000. So, simulation is a really important way of actually getting to learn and experience before you actually have to commit to using resource. And we not only teach within GlaxoSmithKline, but we also do a program for chemists, because as I think Justin was pointing out, the engineers don't get taught experimental design in university, and neither were chemists being taught experimental design by and large. And so we have been working since 2003 with Sue Lewis and Dave Woods on running a program down in Southampton, and not only do the students work through simulations, and by students I mean the PhD students and also professors and lecturers in organic chemistry. They actually get to do, they also get to do hands-on experimentation, and here they're making toast, looking at the factors that are important in making toast. And this actually bears a stronger resemblance to chemistry than the paper helicopters, for example, because you essentially, chemistry is very much about putting your starter materials together, heating them up, cooling them down, and transforming something like bread into toast, and trying to avoid the byproduct, which would be carbon. So as we were doing these simulations and as we were doing this, we were interested in the idea: how far can you push these designs? And we're all aware of George Box's statement about all models are wrong, but some are useful. We wanted to know just how far you could push this, and it was very interesting. I went to a lecture by Ian Cox, who's in the room, and he introduced me to the concept of supersaturated designs. I then was very fortunate to go to a conference in America and see John Saul from the Jump software, or Jump SAS software, talk about supersaturated designs. And these seem to be, a very interesting potential addition to the toolbox, because you're looking at doing studies where you're looking at more factors than you are doing experiments that you've got to run. So that greatly appealed. But of course, when you see something presented by a software manufacturer, you think, is that, I've not seen any other software manufacturer present this, so is this something that's specific to that software, or is this something more applicable? So at this point, I started having a conversation with Dave Woods, and we set up a collaboration with Southampton University, small collaboration. I'm going to hand over to my colleague Kate, who will take you through the story on from here. Yeah. Oh, yes, sure.
Okay, my name's Kate Llewellyn. I'm a research chemist at GSK. I count myself as one of the lucky ones because I came across experimental design as an undergraduate. My PhD was based around experimental design, and I've continued in my career to look at experimental design, with a particular focus now on how experimental design is used in quality by design. So I'm going to give you a live demo of where the supersaturated design that Martin mentioned fits into the workflow that we use when we're developing our chemical processes. So we've got a number of different stages in the development life cycle, but I'm going to talk particularly here about process understanding. And to give you an idea of where the supersaturated design fits into our workflow, I've got a bit of an animation to talk through. So I'm going to pick up my work packages and 3 factors that are key for my chemical reaction. So I start off in the early days, and this doesn't look like it's displaying particularly well. Excuse me, technical hitch. Let's start. So here we are back in Jump 9 rather than an early adopter version of Jump 10. So I will pick up my data set again and pick up the sequential workflow. So the 3 factors that I'm interested in for control of my chemistry, and then the work packages that I've investigated along the way. Okay, so this is looking better. So I start off in the early days with my scoping design, so I'm checking out my ranges, how reproducible my center points are. It didn't give me great information on how to control my reaction, so I go in with a fractional factorial design. This is actually a 5-factor design. You're only looking at 3 of the factors here. And this gives me fantastic information on what actually controls my chemistry. I also found out that I've got quite a lot of curvature. So the next step on the way is essential composite design. And there's a key learning coming out of my screening design that I need to increase my solvent volumes, and I'm operating my response surface design here in a different location within my design space. I've actually done 30 experiments here, which in the chemical world is actually quite a lot of runs. These are conducted on parallel equipment, but the setup time and the analysis time is quite significant. With this information as well, I've got a great predictive model with my central composite design. So I was quite happy to go in for a few of my scale-up opportunities with a very minimal robustness. Scoping robustness, use my predictive model to actually predict what my ranges should be for my plant campaign, what we call a proven acceptable range in quality by design. And this was fine for a number of years, but now I'm actually coming up to filing my project. I really need to know what's my robustness across a number of unit operations. I've only got 3 parameters here involved in my reaction: temperature, reagent and solvent. I've actually got a rather large number of unit operations, 5 or 6 unit operations, each containing at least 3 or 4 parameters. So this is where the supersaturated design comes in, and this is operated for these 3 factors, again in this space here. So you see we're overlapping our knowledge. We're able to use the predictive model to put into some prior information into our supersaturated design. So the supersaturated design was set up as a collaboration with Southampton University, in particular Chris Marley, Dave Woods and Sue Lewis, who've worked on this. This has been a great opportunity to try out something new within our department and influence how QBD is actually done. With Southampton, we were able to share our prior knowledge, so we're sharing the information from the screening designs and response surface designs. And we know really within our reaction what are our active factors likely to be. And this lets Southampton do a simulation study. So they're assessing some candidate designs, and we had a number of runs limit of 10 runs. And Southampton were evaluating both the 8-run design and the 10-run design for the ability to detect known active factors and reduce the type 1 error rate, and also using Southampton's code for the Gauss-Danzig selector to do the analysis of the supersaturated designs. And here's the coded setup for the 16-run design, which was conducted at GSK, and then Southampton did the analysis of the data for us, and through the collaboration we were able to get some really key information on our robustness of our chemical reaction. So to give you the background information, within the screening design, I'm only going to show you one response here. I can see that within the range of temperature, 15 to 35 degrees, increasing temperature is giving me more of my impurity. This is good to know, but actually for other responses, I wasn't getting the yield I wanted, I wasn't getting sufficient conversion of my starting material. So I actually had to operate again at higher temperature, and I also had curvature, so the response surface design was absolutely necessary. Looking at the optimization design, here you can see the real value of the predictive model. So I can see that the relationship between this parameter temperature with my key impurity is really quite severe at high temperatures. This is what we would define as a critical parameter in QBD. Increasing temperature really is going to severely impact the levels of my key impurity. But using the predictive model, I'm able to set an operating temperature range of 25 to 35 degrees. This was tested out in scoping robustness, and this is the range that went into the supersaturated design conducted at Southampton. So to give you the data here, here's the fit of the supersaturated design. And you can see again, the design's clearly picking out the effective temperature. Here you can see my narrower operating region, 25 to 35 degrees, and the key effective temperature here as well. We've also got a minor impact of starting material, but this is only marginally significant relative to the noise and is not something we consider critical. I don't think I've got any more wrap-up slides. So going from ideas to implementation, so Southampton proposed the idea to us of using supersaturated designs for chemical reactions. And we were able to take the research idea, the technical research, and actually really add value to projects within GSK using Southampton's ideas. Interfacing with the statisticians, so making the statistics really work for the chemist, is key here. Previously, we've used traditional designs, and you're often fitting the design to fitting the chemistry to the design problem, either reducing your number of factors to reduce your number of runs, or dropping factors and investigating them in designs that don't fit together particularly well. So some of the other outcomes of the supersaturated design, as well as adding value to the projects, we were able to investigate across a number of multiple unit operations. Actually, for 16 factors, there is no resolution 3 design. The resolution 4 design is 30 runs, and we're able to complete the work in only 10 runs. So as well as taking research ideas and making them real within GSK, we're also really saving a lot of money for the company as well, which is quite key these days.
Thank you. And an important part of this is not just, we didn't just hand over the work to Southampton to analyse. I mean, that's what they did originally, but the completion of this was to actually transfer the way of working over as well, so that we're now empowered to do these type of design setup and analysis ourselves. Mm-hmm. So any questions from the audience?
We do have time for questions. Yep. Start with that.
I'm wondering, you're working in the chemical industry. I guess you're aware of the work on non-linear design that particularly George Box popularised in the 1950s, was when he was working in ICI, specifically for chemical problems. I wonder if you've had any experience using non-linear design and analysis in the work you do.
Is this covered under the closed-loop optimization work we're doing? Is it strictly non-linear design?
It's Kieran's work.
Using chemical kinetic models rather than empirical models.
That is a further extension of our work with Southampton. We have a number of chemical engineers who are interested in kinetics, and our statisticians who are working with Southampton on a current collaboration in that area. Yes.
Very powerful set of techniques. It's very useful for you.
Absolutely. Obviously, we're only looking at one response here, and the trick there is really getting the techniques to look across multiple responses. With experimental design, that's particularly relevant. Obviously, with non-linear models, there's a challenge in
It can
that.
save you a lot of runs because there's no bias potentially. If you choose the right models, it can save you a lot of experiments, and you'll get better models from less data, which is what you're really looking for, I suspect.
Yes, it's what we call, we call them hybrid designs, because you're taking good engineering principles and taking them together with good stochastic principles as well, and building up that combined modelling approach.
Hi. So when you're considering things such as supersaturated designs, how do you assess the operating characteristics of the design so that you know how to saturate? Because ultimately you could go down to an absolutely tiny design, and if it's somewhere the information you're going to get is not going to be adequate. So how do you assess that?
We have covered that as well as part of the collaboration. So with the robustness design, you're looking at narrow ranges where you filter down to a situation where you know you've got sparsity of effects, and assuming you always want to have more than twice the number of runs as active effects, then you're going to point yourself towards a certain number of runs. Where you have a screening situation where you've potentially got a large number of actives, then it maybe you want to think about other types of designs in that case, rather than trying to restrict yourself to a supersaturated design.
So the really key thing that I hadn't appreciated until I kind of came across the presentation from Jump was the importance of the active factors as opposed to just factors. So it's really the ratio of active factors to the experiments, that number of runs you perform, that's the key.
So presumably before you run the experiment, you don't know how many active factors you've got, because that's why you're doing the experiment.
We would always wish to have a good degree of prior knowledge. So here you've seen the sequential workflow that's gone on in advance, And there's a certain amount of univariate experimentation as well that goes into defining those other 13 parameters that I didn't talk about in the sequential workflow. So you already have an idea of what your actives are going to be. And in this case, we're also able to do factor to column assignment. So looking at the VIFs across the different columns and which ones are the best, and assigning our known actives to those columns as well.
It's a really good question, that, because if you start to try and do supersaturated designs at the beginning of the process without that prior knowledge, the chances are that we would actually pick up too many active factors. However, talking to Andy from Lubisol this morning, in his industry, you tend to have sparsity effects in the first place. So in that type of industry, you could actually start with supersaturated designs by first intent as a screening tool. Where we tend to use them towards the end of the process where we've already built up some knowledge.
The question?
I was just curious, you had 16 factors in 10 runs. I think Dennis Lynn's designs could get 80 in 10. I just wondered how... well, yeah, that could be important. They could be the two that are really important. So, but my question was, how different is the one that you showed compared to Dennis's?
Right, we're aware that Dennis's works exist because that was discussed, I think, at this recent, I think it was discussed here in Cambridge. We haven't followed that up yet, and the emphasis is on the word yet. I mean, we've been focusing on how this actually works, and the beauty of this for us at the moment is that it's in a software that we can manipulate and we can work ourselves. I'm not sure whether Dennis's work is done in off-the-shelf software yet. So if it's done in R, for example, we'd have to recode
What
that.
Dennis does is he cuts a placket Bowman array in half.
Right.
And loses the column.
Yeah. The thing, I mean, choosing the actual factors is the key skill. It's the thing that's key to our success is choosing the factors and choosing the ranges to looking at them. And we use all sorts of risk-based analysis in order to choose those selections. And you're absolutely right. It could be in those last two factors. Rather than 16, it could be in the 18 factors. And there's always going to be, you never know, because it could be 20 factors, it could be 25 factors. But at some point, you've got that rate limit, that Pareto effect. It's not likely. It's more likely to be in the ones that you pick up first.
Just one more question from over there, and then we'll...
Right. I was wondering, are you just looking at liquid phase reactions or also gas phase reactions?
We tend not to do too many gas phase reactions in the pharmaceutical industry. You come across 3-phase reactions with solid, liquid, and gas. Is there a particular application?
No, just wondering, how much prior, independent of the actual chemical system, if you have some sort of knowledge about reaction rate constants, which you may, get from quantum chemistry, okay, you may be able to then do something that is similar to what we've seen this morning, where you have a dimensional reduction of your system by just doing a time scale analysis or something of that sort, and then reduce the overall dimension and the number of factors you actually have to look at. And I could imagine that you do this already, but in gas phase chemistry, clearly you have a better chance to actually use theoretical knowledge, whereas in liquid phase chemistry, you find it much harder.
I agree, and I think I want to follow up with Tim and actually see some of Tim's examples in terms of the chemical kinetics and chemical mechanistic examples, and also first principles chemical examples as well, to really to make that real for me, because I can see how the engineering first principles models work, but translating that into my area would be useful for me.
That's the non-linear design I was discussing earlier, is exactly the chemical kinetics, the physics, or the chemical design specifically for that, which is what this gentleman was discussing as well, where you're actually taking the rate constants and such. This was done originally in the 1950s. There's a lot of very good work done on that by George Box and Lucas and people like that. This will help you definitely improve what you're doing.
Okay. Where that works really well is when you're looking at the formation of the product or the disappearance of the starting material. Where it doesn't work as well is when you look at the formation of the many impurities that you form, because there are many reactions and actually having all the rate constants and trying to work out what's going to happen when you've got these in competition with each other becomes very, very challenging at that. So that's why the combination of the techniques is a powerful one.
I think we're going to have to move on. It's good that there's all this discussion, but there is going to be a chance in the later sessions to continue with that. So please join me in thanking these.